Okay, and before we move on, I want to point out this vector field in example 1a, this is going to come up quite a bit. So I want you to notice the properties of it, where the I component is just X, the J component is Y. And I want us to picture what would happen if we extend this in 3D. So here's this vector field here, and then I could say the three-dimensional version would be to let the K component, so first let's go here. Here it is in 2D. Suppose we let the K component be equal to Z. And then we can sketch this, and I'm gonna get this three-dimensional vector field where everything's pointing radially outward. And now if I wanted things to point radially inward, which is gonna happen, for example, when we think about a gravitational field, I could just switch the signs of these, just at least to get the direction. We'll talk about how to scale them to get the right magnitudes. But at least if I switch the signs, then they're all gonna be pointing radially inward. Now, particularly when we model a gravitational field, which we're gonna talk about next, these vectors are gonna get scaled differently because the length of the vectors, the further we get out from the point, like if you think of the Earth as being at the origin, the further away we are, that force of gravitation is going to be less, so our vectors are actually going to be smaller. So let me show you exactly how we create that vector field for gravitational force. Okay, so the gravitational force of an object of mass little m, so let's suppose that you're at the point x, y, z, and you're some mass like out here, little m, due to an object of mass big M, we're going to put that at the origin, like the Earth, is given by this vector field, where we define G, which is a vector field here, to notice here's the X, Y, Z vector field. That's the one pointing radially outward. And then we're going to scale that by its magnitude so that this whole thing right here becomes a unit vector. And in fact, we have a name for this. In physics, usually they're calling this r hat. I want to point out that this is not what we would call r hat. We would probably think of this more as like rho hat if we were to define rho as a vector, because in physics, they're defining this distance between the objects to be little r. We're defining that to be rho. So I just wanted to clarify this is rho. But it's fine if you're used to seeing this from the physics notation. I just wanted to connect it. So this here is a unit vector. And then this is going to be giving you the magnitude of that gravitational field. And you can see it's proportional to the distance, 1 over the distance squared, because in the denominator here, I have r squared. And that's how the further away that we get here, your vectors are getting shorter because the magnitude is getting much smaller the further away you get. Now in physics, you're going to see them using the notation, let's rewrite it here, that G, your gravitational force, or excuse me, your gravitational field here is going to be negative. Okay, this capital G is a known constant. This is the universal gravitational constant, and it's given by this here. And then capital M is going to be the mass of the object. In this case, we're going to think of it as the Earth, and then divided by the distance squared between the objects. And then here's your unit vector to help you get the direction. Now, most of the time when you've seen G in physics, like especially in high school, most of you are going to say, well, G is just negative 9.8 meters per second squared. And I want to connect that to where that's coming from. What's happening is near the Earth's surface, we can notice that this vector field is going to appear to be uniform. And we can actually even plug in some of the values. So near the Earth's surface, the distance, r, is going to be 6.37. And we know the mass of the Earth. So we can then define G to be, put this here again, we'll actually plug in what those values are. But the key thing we're going to change is instead of saying, oh, the direction is r hat near the surface of the Earth, that's going to look like over here that it's just coming in the direction negative z, right? So my vector, my unit vector here would actually be k hat instead of r hat, when we're near the Earth because it looks like it's coming in a uniform field. And then we can plug in, we're going to call this whole piece in front of here little g. So we really call this negative little g, not a vector anymore, just a constant. And then k hat, where little g, we're going to plug everything in, plug in the universal gravitational constant, the mass of the Earth, which is right here, divided by the radius squared, and that's where you're getting that 9.8. So I wanted to connect that this is actually just a special case of this universal gravitational vector field or force field up here, where we actually have a radial field. But for most applications on Earth, we just simplify it to this and say that the gravitational force is 9.8 meters per second, and then it's pointing downward. Okay, before we move on, because we're going to do some applications now, I want to just connect this to a couple of other vector fields you may have seen. So we've talked about gravity. Let's also talk about, we use vector fields, or we can use vector fields to describe velocity of fields. For example, wind, we can use it to describe the velocity of water. We can use it to describe the velocity of wind flow around an airfoil. We talked about gravitation, we can use it to describe electric fields, as well as magnetic fields. There's another electric field described by a vector field, magnetic fields. And then lastly, you actually have been working with vector fields starting last chapter. And what I want you to recall is we could find at a given point a vector that represented actually something specific, and that's the gradient. We can think of the gradient itself as forming a vector field if we were to plot the gradient at a bunch of different points. And in particular, last chapter we learned that thinking of this blue surface as one level surface of a function of 3 variables, then the gradient at any given point is going to be normal to that surface. And it itself forms its own vector field. We're going to use that coming up a lot in this coming chapter. So now let's move to a specific example of what we'll do in vector fields, which involves finding the work done along a curve.